In our last lesson, what we looked at was relationships. Okay, and the relationships we looked at were described by a rule. So this is a relationship here, and it basically says that there's a relationship between y and x. That is, if x is 1, y is going to be 2. Well, some relationships can also be described as functions. And so today what we're going to do is formalize our definition of a function and look at the vertical line test as a way to describe or to check whether what we've got is indeed a function. So what is a function? It's a special type of relation, okay, or a special relationship. And I'm sure I've used it before and I've used it many times, but the thing about this is that every relation is not a function, okay? So there are some relations that simply can't be classified as functions. So here's the definition of a function. This is what it boils down to. A relation that produces a maximum of one y value for a given x value is a function, right? So basically it's saying that if you jam in x into a function and it spits out only one y value, then we've got a function. So again, what it is, it's like a machine, or what is a function? It's like a machine that has an input and an output. So in a pasta machine, you put in pasta dough and it puts out some form of pasta, okay, whatever, tortellini or I don't know, whatever. So imagine the pasta machine accepted pasta dough and then produced both fettuccine and linguine at the same time. How could it? It either produces fettuccine or linguine, i.e. it can't produce two different things. So when I put one thing in, one thing comes out. So what we're going to look at is which of the following relations are functions. So all of these are considered relations or relationships, but which one's a function, okay, or which ones are functions. So let's have a look at this one here. So when I put -3 in, it produces -4. When I put -1 in, it produces -1. When I put -6 in, it produces 7. And when I put 1 in, it produces 5. Now notice that for every x value, I produce only one y value. This thing here is a function. All right, let's look at this one here. -4 produces 1. -4 also produces -1. That's confusing. So the same input, -4, produces two different outputs. This is not a function. Okay, this one here, we can see that we've got a linear function here, and for any x value, it produces only one y value. It's a function. Okay, this is a parabola, same thing. So when I put in an x value, I'm only going to get a maximum of one y value. Okay, so this is a function. All right, this thing here, what it is, not sure, but it's not a function. Why? Because when I put 4 in, it produces this value here, +2, and it also produces -2. Okay, for 6, it produces this and this. So for an individual x value, I produce two y values or two different outputs. This is not a function. There's nothing wrong with it. Okay, there's nothing wrong with that graph there. That's a good relationship, but it's just not a function. And the circle is also not a function either, because when I put in -2, it produces this y value and this y value. So it is not a function. So essentially, to diagnose or to see whether a relation is a function is you perform what's called the vertical line test. What is it? If it's very technical, very technical. All right. Don't know whether you can get my sarcasm there, but if a vertical line can be drawn anywhere on the graph and it only ever intersects the graph once, then the function or the relation is a function. So see how I draw a vertical line there? Intersects twice, not a function. Draw a vertical line, draw a vertical line, draw a vertical line. I can only get a maximum of one intersection, therefore function. So once we know what a function is, we can use this function notation. We've been using this heavily, so this should all be revision. So we've got a function y equals x plus 1. Remember, we can say that the y value obtained is a function of the x value, okay? So we use this notation. We simply replace y with f of x. Yeah, that's how we pronounce it, f of x. So the ease in which we can do things with function notation is just magnificent. So f of 3 means we want to put 3 into this function here. So I'm just going to go 2 times 3 plus 3. So the input is 3, and what comes out of the function is 9. You can put all sorts of things in, put anything into a function, as long as it'll accept it in its domain. But anyway, so this one here is going to be 2 multiplied by x take 1 plus 3. Let's rewrite that as 2x take 2 plus 3, 2x plus 1. Now this one does not mean to put 0 into the function. What this says is when or for what value of x will the function be 0? So let's find out. So what we're going to do is let the function, which is 2x plus 3, equal 0. And this is basically asking the question, hey function, when are you 0? So if we solve for x, what we're going to get is the value. -3, x equals -3 on 2. All right, now what we're going to do is jump into some more sophisticated notation, okay? So when we've got a function, there are special names for what can go into and what can come out of a function. What can go in? Well, we know that that's the domain, okay? What can possibly come out of the function is what we call the codomain, okay? Now, this is where it gets a little bit odd, but we know that what actually comes out of the function is called the range. These are the things that it can produce, but the codomain is all the possible values, okay? Now, we've got a basic structure for writing functions, and it looks like this. We have a function name, maps to the domain, or the domain of the function maps to the codomain of the function, and then we write our function. So how do we do this? This is a function, g, such that it has a domain of 0 inclusive up to positive infinity, which maps to the codomain, which is a set of all real numbers. And our function name is g of x equals x squared. All right, now I don't want to talk too much about the codomain because in maths methods, we always mapped the domain to a codomain, which is a set of all real numbers. And I'm trying to think of an instance where it might elsewhere map to something else. And I think it might map to, in other functions, it might map to the imaginary number system or something like that. But in mathematical methods anyway, we only deal with the real number system. So we can always put the codomain as R. The domain of the above function is abbreviated to DOMG, or X is an element of if we're stating it, and the range, we can say Y is an element of, okay? And we have an alternate way of writing functions. So I kind of call this, and this is not proper mathematical speak, but I call this writing the function with the whole kit and caboodle, all right? So if we've got this relation here with a domain of R, we can write this in full function notation or with the whole kit and caboodle as f is a function such that it has a domain, which is a set of all real numbers, mapping to the codomain, which is a set of all real numbers, and our function is called f of x equals x squared. So here we've got a linear function. It's got a domain from 0 to 4. So let's write this up, and I'm going to call this function g such that. I'm going to call this one g of x. Now, what's its domain? What's this thing here? 0 to 4. This maps to the codomain, which in methods is always a set of all real numbers. We have a comma, then we call our function what we want to call it. In this case, it's g of x equals 2x take 1. Here's a hyperbola with this domain. So let's call this one h. Okay, I can call my functions pretty much anything I want. So h is a function such that it has a domain, which is a set of all real numbers not including 0, which maps to the codomain, which in maths methods is always the set of all real numbers, and my function h of x equals 1 on x. All right, my puppy is scratching around in the background there, so I'm just going to pause this and move him out of the room. All right, for this next one, what we're going to do is write this in full function notation. Okay, so remember that or full function notation will just be a bit more than just writing f of x equals. Okay, so we've got to get it in f such that. Right, so this first one here is a linear function, and it's got no domain restrictions. So we're going to say that, we'll call this one f of x. So we'll say f is a function such that the domain is the set of all real numbers mapping to, in methods, remember the codomain is always the set of all real numbers, where f of x is negative 3x plus 2. Okay, for this linear function, we've got a restricted domain. So we're going to call this one, let's call it g, is a function such that it has a domain of 0 to positive infinity, mapping to the codomain, which is a set of all real numbers. G of x equals negative 2x plus 5. For this quadratic function, we've got all the values between negative 1 and 2 in the domain. So we'll call this g, we'll call this one h, such that negative 1 to 2, mapping to the codomain, which is a set of all real numbers, h of x equals 5x squared plus 6. And our last one, d, this truncus, we'll call this one hij, k, let's call it k. Okay, you can call the function whatever letter you want. So k such that we're going to put or allow the set of all real numbers not including 2 in the set, mapping to the codomain, which is a set of all real numbers. K of x equals, get rid of the calculator, equals 1 over x take 2 all squared. Okay, so using function notation. So here's a function, f of x equals 2x take 4. We want to find the value of f of 2, so let's do that. So f of 2 equals 4 take 4 equals 0. F of t equals 2t take 4. That's all we can do with that. B, find the value of x for which f of x equals 6. So let's replace f of x with 6 and ask the function, what value of x are you 6? So it's going to be 10 equals 2x, x equals 5. So when x is equal to 5, the function's value is 6. C, find the value of x for which the function is equal to 0, or in other words, find the y-intercept. So it should be negative 4. Let's do it. 0 equals, no, it shouldn't. That's when y is equal to 0. This is finding the x-intercept. So 0 equals 2x take 4, 4 equals 2x, x equals 2. D, what values of t is f of t equal t? So let's go t equals, and f of t is going to be that with t in it. So 2t take 4. That's going to be t take 4 equals 0, t equals 4. E, what values of x is f of x greater than or equal to x? So this is f of x. F of x is 2x take 4. And we want to know when that is larger than x. Okay, so let's subtract x from both sides, and we're going to get x take 4 greater than or equal to 0, x greater than or equal to 4. F, for what values of x is the function, i.e. 2x take 4, less than or equal to 3x? And that's going to be negative x less than or equal to 4, x greater than, because I'm dividing by a negative in an inequality, so I need to flip the inequality, x is greater than negative 4. Okay, so sketch the graph of each of the following functions and state the range. For this, we're not going to really do a full sketch for this. We're just going to sketch so that I can actually pull out the range. And so, yeah, I'm not going to do all key features and all that sort of stuff. All right, so this is f of x equals x. Okay, so that's the function y equals x. And we're going to jam in -1 into the function, which is going to be -1, and 2 into the function. So let's put in those endpoints. And it runs through the origin. All right, so the domain is x as an element of -1 to 2, and the range y is an element, or f of x is an element of also -1 to 2. Okay, we've got a quadratic between -1 and 1. So let's just go f of x equals x, x plus 1, 0 equals x, x plus 1, x equals 0, x equals -1. So 0, -1 are the intercepts. -1 to 1 is the domain. So what it's kind of going to do is go like this, up to there, and chop there. All right, so that's what it's going to look like. Now, how to sketch this thing? And that's going to be, when I put 1 into this function here, it's going to be 2. So that's 2, or 1 comma 2. So what I need to basically find is the turning point and up to this point here to get the range. So the range is going to be y as an element of this value here all the way up to, and so that's inclusive of that value, and up to and including 2. So I just need to work out this value. How am I going to get that? Well, what I'll do is I'll just quickly complete the square on this. That's y equals x squared plus x plus a half squared, take away a quarter. And that's going to be y equals x plus a half all squared, take away a quarter. Okay, so this is the one I'm really interested in here. That's how low it's going to go, at -1/4. So -1/4 is the y value. Okay, for D, C, I missed that one. For this hyperbola, what we're going to do is it's from 0, not including 0, up to 2. So it's going to be asymptotic, and then when I put 2 into it, it's going to be half up to there. Okay, so our range y is an element of, so the lowest value that can come out of this function is a half, and what it will do is then tend closer and closer, infinitely close to 0. And when it tends close to 0, these y values will approach positive infinity. Okay, this one here is a parabola, and similar scenario to this one here. Don't actually really need the x-intercepts. Don't think it has any anyway. So all I'm going to do is find the turning point of this, and then take the values from the turning point upwards, because it's an upright parabola. So let's just do that. Y equals x squared, take 2x plus 8. Y equals x squared, take 2x, halve it, square it, 1 squared, that's 1 squared, take 1 plus 8. Y equals x take 1 all squared plus 7. Okay, so when 1, 7, that's its turning point. It's going to continue up from there. So the range, y is an element of, lowest value is 7, highest value is positive infinity. All right, so here are your questions to answer after you've taken the notes down, and don't hesitate to contact me if you've got any questions that are based on this work, or any other questions that are based on any of the stuff that we've done so far.